about a concept called research ops. And this is sort of a collection of concepts together with some solutions, things that I've learned over the years doing scientific computing, both in academic and non-academic spaces. Some of the central problems that I'm going to be focusing on here are about some of the additional challenges that we have to face when we're doing research, aside from the actual main research problems. So just to give a brief introduction, I'm going to be co-presenting today with my colleague Venkat Bala. We both work at a quantum computing startup called Agnostiq, which is based in Toronto. I've been there for about a year now, Venkat for a few months. Both of our backgrounds are classical HPC, and we both have done PhDs in physics. So we're both familiar with the space at this point. I'll just give a brief overview of how this talk is structured. First, I'm going to sort of introduce what research ops describes. So it's sort of a shorthand for computational research operations. Then I'll talk about a tool that we have built called Covalent. And this is a workflow orchestration tool for quantum and HPC. And I'll go into that in more detail later. Then we'll spend a whole bunch of time on code examples so that you guys can see everything in real terms. And I'll mention now that all of this code is going to be provided on GitHub, both during the talk and after the talk. And given that we have two people presenting, if you have questions about how to access anything or do anything during this presentation, you can post a message in the chat and one or the other of us can answer it. After this, I'll be talking about HPC in the cloud and beyond, sort of some of the nuances and difficulties about how HPC is evolving in different spaces. And then finally, we'll do a hands-on tutorial focusing on molecular dynamics and specifically focusing on the operational challenges in such an experiment. So let's get started with computational research operations. So why is computational research hard? Now, if you're going into this as a beginner grad student, of course, you're going to be thinking about these items on the left here. These primary challenges, you want to explore new research problems. Perhaps you want to apply some interdisciplinary techniques. You want to maybe push the boundaries of hardware to extend some results from a previous paper. You want to find some hidden patterns in data in the case that you have really large data sets. These are sort of the big picture goals that we're trying to accomplish. And of course, the output of this is going to be new scientific results, research papers, new collaborations with people. These are really what we're aiming for with computational research. However, there are all of these additional operational challenges that come along with this. And these are things that everybody has to face at one point or another. Things like organizing and versioning your experiments, managing and sharing your data, managing accounts on multiple clusters if you have multiple cluster access, checkpointing long simulations so that if you have to run an experiment for a month and it fails halfway through, you don't lose all of your partial results. Reproducing even your own work can be difficult if you come back to it months down the line or even a year or two down the line for reasons such as package version conflicts, compiler versions changing. So there's a lot of documentation that is required just to do computational research. It can be very difficult even to incorporate legacy code into new code bases. So suppose that you want to develop a new scientific computing package, but also include some legacy code that has been handed down from an advisor. If it's in a different language or if it uses different package versions, it can be difficult to reconcile it with your own software. On the end of this, you also might be thinking about identifying optimal hardware resources. So if you're doing a particular scientific experiment and you have access to an HPC cluster, there may be a whole bunch of different queues that you can select from. And it might not always be obvious which one to select. I know in my own personal experience, I pick the one with the shortest queue time and that meets the minimum requirements. But in the big picture, we might also be thinking about working within budget constraints. How do you get the most research data for a particular research budget? And certainly, if you're doing research at a company, this is going to play a much bigger role. For all of these items on the right-hand side, it's a lot of work with little reward. And everyone comes up with sort of their own little bespoke solutions to these. I know I did. I know Venkat has done some similar stuff. But ultimately, it's very difficult to achieve what you're trying to achieve in the big picture, the things on the left, while spending so much time tackling the things on the right. So what we're trying to deal with here is a way to automate or standardize some of these things on the right-hand side so that we don't spend our brain power even thinking about them. The next piece of this that I want to introduce are that modern computational workflows are complex. So what is a workflow, first of all? A workflow is, most simply, it's a set of tasks with dependency relations. So if you are familiar with any sort of functionalized code, you'll probably be familiar with a basic workflow. You might have some machine learning problem. Maybe you spend some time collecting data. You spend some time cleaning the data. You spend some time training a model. You spend some time testing the model, analyzing results. These are all different steps in a workflow. And the reason that modern workflows are complex is that we have access to so many different resources. Some of these resources might be HPC clusters at a university. Others might be HPC clusters at a national lab, and they might use different schedulers. Other resources might be HPC on the cloud. You might have some tiny local cluster in your lab. You might be interacting with quantum computers even these days, which have their own queues and schedulers. And it can become very difficult to manage the data transfer, manage code versions, and just manage your experiments in general. Because if you need to reproduce something, now you have to remember how you interacted with all of these different devices at a given point in time. So really, this is the challenge that we're trying to simplify through good research operations. On top of all of this, quantum computing is driving the need for more heterogeneity. So if you're familiar with some of the near-term quantum algorithms, you'll know that they're all variational in nature. They all require both classical and quantum resources working together. On top of this, the way that we interact with quantum computers these days is through APIs. So you'll send some quantum circuit to a particular quantum backend, and it will wait in queue until you're able to query the result. The problem with this is that the queues can be minutes sometimes, or they can be hours. There may be unplanned outages. Unlike with Slurm, there's no good way to get a sense of what's the current load on the system, because really there's no standardization. If you use IBM quantum computers, you'll get some piece of information, maybe the number of people in queue. If you use Rigetti quantum computers, you might get an estimate of the wait time, but really not have an idea of if that includes reservations or not. If you use D-Wave quantum computers, you'll get completely different information. And so the problem there is that your classical resources are going to be waiting for a very long time. Now, this becomes important if, for instance, you're doing something involving model training using a GPU. So suppose that your classical resources are using GPUs and you're making calls to a quantum computer. And you have this back and forth in the variational loop. What that means is that you're consuming lots and lots of GPU core hours just waiting in queue. And so one of the advantages of good operations is that you can insert a broker device to communicate with both of these. And this can be your laptop. It could be something very low compute, low cost. And so really, the idea here is that just for basic quantum computing, you already have to deal with at least 2 or 3 different devices interacting with each other. And it can be very difficult to manage. So one of the tools that we developed internally at Agnostiq for our research operations is called Covalent. Covalent is right now an open source and free workflow orchestration platform for heterogeneous computing. So specifically what I mean by this is that for the academic community, for researchers, for open source contributors, for individuals, it will always be open source and free. So certainly for this audience, if you're interested in looking at the code, if you're interested in contributing, you're able to check out our GitHub page mentioned at the bottom here. So what is Covalent? Covalent is a unified interface to deal with research operations. It allows support for both quantum and HPC, which is very different from other workflow tools. This quantum introduction is something that you don't find, as far as I know, in any other workflow tools. It's specifically geared for distributed computation and very heterogeneous hardware and software resources. And so the idea is that you have this covalent tile in the middle of this diagram. And this is the one place where you're able to manage everything from resources to versioning to everything else. As you can see in this left-hand side column here, it works on top of other languages, other schedulers, and other packages. And we'll go into details about what that specifically looks like. So most simply, Covalent exists because in practice, we tend to spend a lot of time writing code, debugging code, executing code, maintaining code, but not actually time on differentiated research. And so what we found is that by working with some tools which standardize this, it allows us to change what this chart looks like. It allows us to spend most of our time on research and much less time on operations. So there are sort of 4 scenarios you can think of that might apply to your own work. In one case, you might be doing hybrid research or experiments. So for instance, if you're doing quantum machine learning, and we'll see an example of this in the talk this afternoon, a single quantum machine learning experiment could contain resources that include CPUs, GPUs, TPUs, and quantum processors as well. This can be very difficult to manage otherwise in a cost-effective way. HPC research can also require rapid prototyping and experimentation across different software parameters. So as an example, you're exploring some model. You might be interested in understanding, what are the different parameters that you want to explore, what areas of phase space, and you really don't know what the right parameters are going to be until you've explored a broad set of them. And so this is where rapid prototyping comes in. You really want to be able to execute the same code over multiple runs, but in a way that's organized so that you can pull out the useful data and throw away the data that's less useful. In the third example, you might be interested in high throughput calculations. So once you do understand exactly how you want to run your model, and you have the exact idea of that one plot that's going to really distill your conclusion in a paper, you're going to need to run something at scale. And this means running it, running massively parallel jobs. Oftentimes in HPC, we use MPI or OpenMP in order to scale across different devices. But beyond that, that's sort of with a view towards one cluster. If you want to be able to use multiple clusters, and this is something that's increasingly important as supercomputers are no longer able to scale due to power considerations, then it becomes important to use tools which allow you to manage experiments across clusters at a layer on top of Slurm. The fourth solution here is what I mentioned, of course, previously with the quantum stuff, is that there are often long HPC queue times. And so if we are trying to reproduce some experiment, it may no longer be feasible to run it with exactly the same hardware. So as an example, when I was working at Perimeter doing a postdoc, I had access to 3 different HPC clusters through the institution. And these were all very large clusters. They were great to use, but the queue times would vary dramatically. So I might run all of my experiments on one particular cluster, get all of my data. And then by the end of it, I would find, well, actually, out of 10,000 experiments, 100 or 200 of them failed for whatever reason. And I would need to rerun those 100 or 200. But it turns out it's no longer feasible to do it on that cluster because now the load has increased by a lot several days later. And so really, I want to run it on a different cluster. The problem with that is that now I have data on multiple clusters. I have 2 different versions of my code on multiple clusters. And again, you have to sort of develop your own methods and solutions in order to deal with this so that you don't lose data, you don't lose changes to code, because that does happen very frequently. So let me give you some context about where this solution fits in the Python stack, at least. At the lowest two levels in the stack, we see tools for parallelization, meaning you want a task to run on multiple cores, or distributed computation, meaning you want your code to run across multiple devices. People who are HPC power users are probably familiar with this OpenMP plus MPI experience, which allows you to achieve the same thing. Those are sort of lower level equivalents to some of the tools that you see here. But the point is that those are tools that are used to make your computations run faster across essentially the same hardware. At the top of the stack, you have tools that are designed to make your computations manageable. These are commercial industry-grade workflow management tools. As an example, suppose you have a recommender system like as is used in Netflix. Netflix has to retrain machine learning models on a schedule every day without fail. However, the actual workflow that it's running is not changing so much. The parameters are not changing so much. The difference here is that those are very large tools. They're very difficult to use. They're designed to run tasks on a schedule as opposed to running tasks in different locations. And so what we have here with Covalent is something at a layer in between these two other layers in the stack. This distributed workflow layer allows you to work on pre-production code as opposed to production code. And what that means is if you're doing research and development, if you're doing academic research, for instance, you're going to want tools that allow you to really rapidly run lots of experiments and explore your parameter space. As an example, like with Apache Airflow, which is a very standard and somewhat old tool at this point, it takes up to 10 seconds to run each job to dispatch it to the server. The difference with Covalent is, of course, it takes fractions of a second. And so if you're running tens of thousands of experiments in order to understand a particular application, this becomes very important in terms of saving time. I'll just briefly mention this because we'll go over it later in the code examples, but Covalent is supporting a growing ecosystem of hardware and software. So we interface with lots and lots of different hardware backends. Everything from HPC schedulers like Slurm or LSF, stuff on the cloud through AWS, Azure, and GCP, Kubernetes clusters, all sorts of different quantum resources. So we're beginning to see containerized solutions emerging in the quantum landscape, such as AWS hybrid jobs, Qiskit runtime. So those are solutions that containerize a task almost as if it were a Docker container. It includes both the classical and the quantum part, and then it deploys it through an API call to either IBM or AWS, and they run it on their infrastructure. And they deal with all of the queuing as opposed to you dealing with the interacting between the classical and quantum resources. That's a very interesting space if you want to check it out, but it's something that's evolving very rapidly, and certainly there's no standardization yet. The last bit I'll mention here is that, of course, we support different languages because nobody practically, realistically, is going to do all of their HPC in Python. And so we've spent a lot of time building out interfaces between Python and other languages like C, C++, Bash, Julia, Fortran, etc. So the last few things I want to talk about before we go into some research applications are some of the concepts that we'll use. So I mentioned this on the workflow slide, but the workflows are simply comprised of interdependent tasks. We have used terminology here adapted from condensed matter physics. So if you're familiar with crystallography, you'll know that electrons form these lattice structures. And so we sort of use the same terminology where electrons represent these atomic tasks and workflows are collections of these that form lattices. The tasks can be written in other languages. I said that. They can run on different hardware backends. And one of the most important points here is that the things that are passed in between different tasks are Python objects. And this is, again, very different from other workflow tools. And it's, in fact, non-trivial to implement this because if you have different hardware backends and different software environments, it's not always easy to make sure that you can serialize and deserialize Pythonic data. But this is again, an area that we're working on improving support. One of the key components of this, for good research operations, like I said, we don't want to spend any time, if possible, on research operations. So what we thought of is, what's the minimal amount of code that we can ask people to write in order to, sort of operationalize their code, make it compatible with a tool that addresses this. And what we came up with was basically one line additionally of code per function, per task. So what we see here is if you have functionalized code on the left, so you have some particular task which does an optimization routine, maybe you have another task which does some model training, what you're going to add on the right-hand side are just these Pythonic decorators. And what those decorators do are they take this function and they attach all sorts of metadata objects to it. So under the hood, this really turns into a class object instead of a function. And the advantage there is that it allows us to store, together with an instance of a function, it allows us to store all of the metadata about how it ran. So this includes benchmarking information. It includes profiling information, which is an area that we're currently working on. It includes where it ran, basically everything you could think about. Beyond this, these can still be called as regular Python functions, without using any of the server. But if you want to dispatch it to the server, then you finally just use this dispatch call at the bottom here. And the advantage of just those few lines of code changes are that in the user interface, you can view all sorts of information. So this is an example of what you might see for a particular workflow. You'll have these boxes here which represent different tasks. Everything on the left-hand nav bar is going to represent workflow level metadata. So like you might be interested in viewing the actual results within a browser-based UI, benchmarking information, where your log files ended up. And the advantage to having a good visual representation of your experiment, again, from an operations perspective, is that it allows you to more clearly communicate to other people how your code works. So if you want to explain to somebody, this task over here is, the one that's the bottleneck in my code, or this task over here is the one that costs the most amount of money, or this task over here, maybe we should take another look at it. It throws errors sometimes. Because really, what are the alternatives? The alternatives are you can give somebody a paper from archive and have them read about an algorithm, or you can show them the source code. And both of those take time to process. Whereas a visual representation of an algorithm, like you see here through this directed graph, really distills what's happening to somebody else. So it's really valuable, in my opinion, for collaboration as well. I mentioned this before, but there's also the ability to look at task level results in metadata. There's some project management tools. I won't go too much into this. The main thing I want to emphasize here, again, it's open source. You can contribute. We welcome contributions. And we want this to be a tool that is valuable for the academic community in particular. Okay, so let's go into some code examples now that I've sort of explained how we're addressing these operational challenges. So let's take a very basic example here of curve fitting. So the first step that you might do, suppose you have some Python script already. It looks something like what you have on the left. This is very common in computational science. You have a whole bunch of scripts. If you want to modify anything, you open it up, you change some values, you rerun it. So the first step that you're going to do is what you should do for any good code, which is to functionalize it. You might be asking, well, how do I know if it's one function or if it's two functions? And really what it comes down to is isolation of data and isolation of required resources. So if you have a particular block of code and you say, well, this block of code is modifying just a particular portion of data that's not referenced elsewhere in the code, or if this block of code has particular resource requirements, like for instance, you want it If it's using TensorFlow, maybe you want it to use GPUs, or you want it to interchangeably use GPUs and CPUs. That would be a good candidate for an isolated function. So again, this is really just general computer science stuff here. It's not really physics in particular. The next thing that we do is we add the decorators to the function, like I mentioned before. So just one line of code on top of each function. We're going to create the workflow. Again, it's all Python. The main difference between what we're doing here and what you'll see in other operational tools for workflows is that oftentimes this workflow creation step is done in something like YAML. It's done in a non-Pythonic way. So really being able to do this in Python where you're just calling your other functions as if it were any other Python function is something that distinguishes this tool from other tools. Next, we're going to dispatch the workflow with a particular set of input parameters, and then we're going to query the result, and this wait equals true indicates that we should block the command until the result status is completed. Next, we can view the results in the UI, so this is actually what it would look like for this particular workflow. Something that I find particularly valuable are just looking at the particular inputs and outputs, or being able to look here at like, where was the log file stored? And this isn't necessarily a big deal if you're just doing experiments here or there, but if you're rerunning code hundreds of times or thousands of times, it can be very difficult to manage your log files or recall what the outputs were without rerunning experiments. And so this is designed to simplify that. And the output in the end is, like I mentioned, it's a Pythonic object. So you get a curve fitted plot, and you could just do get result. It'll return the plot object, and you can do plt.show, and it shows this, and you can just do it right in a Jupyter notebook. So it's very straightforward. So let's go to something that's a little bit more interesting and substantial. Let's talk about classification using support vector machines. So this is a particular machine learning method that's quite popular. We're going to be looking at an example where we want to recognize handwritten digits. This example here was adopted from the scikit-learn tutorials. So you can go onto their documentation as well if you want to learn a little bit more about how SVMs work. We're not going to be going into the algorithmic details here about what is SVM, but really talking about what are the steps to working with an SVM classifier, and what is the data that's passed around. So the data set here is going to consist of a set of 8 by 8 pixel images of digits, as shown on the bottom here. So of course they're blocky, they're blurry, but the labels here say that they represent 0, 1, 2, 3. And so the data set is going to consist of pixels with different degrees of shading. So the first step that we want to do is we want to load the data set. In typical real world examples, this data set can come from the internet. It can come from a database. Maybe that database is local. Maybe it's something remote that you connect to, or it could just be a file on your system. So in this example, it's the simplest of those. It's just a file on your system. So we're going to load this data set, and it's going to appear as an array here. The next thing that we want to do is build the SVM classifier. This classifier takes in a single hyperparameter called gamma here. And using sklearn, it's really quite simple to do an SVM classifier. So we're working at a layer sort of on top of TensorFlow or PyTorch, where we really have to do very little in order to build and study this model. So this is how you might interact with these types of machine learning models in the real world if you're prototyping something. The next thing we're going to want to do is split the data set into training and test sets. A typical machine learning example might say you take like 80% of the data for training and then use the remaining 20% for testing. Next step is that we are going to train the classifier. Most often, the training step is going to be the most computationally intensive. And so for this step right here, we're going to be interested in asking, can we easily modify the code so that instead of running locally, it runs on a cluster with a GPU? Or instead of running on a cluster with one GPU, it runs on a cluster with 8 GPUs with very, very minimal code changes. And the advantage there is that most of the time you're going to want to write your code and debug it and test it just on your laptop without interacting with any of these resources, because you don't want to wait in queue time. And so once you're done with that, you're going to want to deploy it to a cluster. But we want to abstract away the details of which cluster or which partition, etc. The last step is that we're going to get the model predictions here. And then the final step is to generate the classification report, which is going to tell us how the model worked. So let's summarize what this workflow is. The workflow takes a single input parameter, which is for the SVM classifier. We're going to load the data set, build the classifier, split the data, train the classifier, and do some predictions. One thing I want to point out here is that another advantage of thinking about scientific research in terms of workflows is that if any one of these steps fails, traditionally you would have to rerun the whole thing. However, with workflows, you can resume from the last step that completed successfully and retain the data. So the checkpointing is really built into workflow systems in general. And it's something that we like to take advantage of here. For instance, if there's a typo in the prediction step, which is a very low compute step, we don't want to have to retrain the classifier just to get that last step to run again. So now we're going to run this workflow with a hyperparameter of 0.001. You get the result. You can see an example of what this workflow looks like here. Again, this is using the user interface. This on the left-hand side, you can see the inputs and the results. So even without interacting with code, you can very quickly communicate what are the results and very quickly distill the correctness of each of these tasks and of the workflow itself. Finally, the classification report. Of course, we want to take a look at this. Mostly, I want you to look at this first column here, which is the precision, which says that for number 0, we were able to identify it 100% of the time perfectly. For number 1, we could identify it 99% of the time perfectly, and so on and so forth. It looks like 9 was the worst here. The next topic that I want to address here is the idea of sublattices. So sublattices play a role when we have a workflow, but now we want that workflow to become a task in a different workflow. So as an example, you have a workflow which trains the classifier for a given value of gamma. If you're exploring the phase space of any application, you're going to have some values, temperatures, learning rates, whatever they are. And you're going to want to explore across that parameter space in order to know really where you want to drill down for your really big deal experiments. So what we do is we take this lattice, we add an extra decorator on the top of it, another electron decorator, and that's it. Now it becomes a task that can be included in a different workflow. And the point of this is that for code in general, you want it to be modular, but you also want it to become building blocks in other code, so that once you have code that you trust, that you've tested, that you know works, you want it to be something that you can actually reuse in larger experiments without doing tons of modifications to the original code. And again, this is all to simplify the operations of your research so that you're spending time drilling down on what the right area of your phase space is, as opposed to constantly editing your code and trying to recall which parameters you used. So in this larger workflow, we're going to do this task called find best gamma. And so this is going to iterate over a particular set of values. Here you can see we use 0.001, 0.002, 0.003, and 0.01. But this could be a much larger list if you like. This is going to submit the workflows as a series of workflows. So at the very bottom here, you can see the one that was first submitted has 16 tasks in it. And each of the sublattices, as they are workflows themselves, also have a record in the workflow database. So these all appear here. And your research problem now looks quite a bit larger. Again, it can be difficult to disentangle dependency relations without a good visual representation. Okay, so at this point, I'm going to pass it to Venkat, my colleague here, and you can take it away. I will disconnect.
Can you hear me, Will?
Yeah.
Yes.
Okay, cool. I can share my screen. Okay, just a sec. Okay. Can everybody see?
Yep.
All right, cool. So, okay, so in line with talking of code examples, so the next one we sort of wanted to present was at the earlier slides, Will alluded to the fact that using covalent and using when workflows get really large and we have these heterogeneous landscape of compute devices that's available to us, multiple HPC clusters, the cloud, or even quantum devices. Once a workflow is built, covalent can be leveraged to tell which particular tasks of a particular workflow needs to run where. And for example, I mean, I've chosen this example. We've chosen this one particular example called Bohemian eigenvalues. This was sort of a research topic that my colleague, when I was doing PhD, was sort of interested in, and all the details are actually available at this URL. Basically, all this entails is Bohemian stands for bounded height integer matrix eigenvalues. Now, basically, all that is like a family of Bohemian matrices is just a distribution of random matrices where the matrix entries are integer and they are sampled from a finite set of bounded height. So the integers are never, growing really out of bounds. And the other key thing that sets apart these kind of matrices is like the discrete set from which these matrices are built is independent from the dimension of the matrix. So basically, if, in this example, we'll be creating a 5 by 5 random matrices using a set that's just 3 numbers, -1, 0, and 1. And Bohemian eigenvalues are nothing more than just eigenvalues of these Bohemian matrices constructed in this way. And the reason we chose this example is because in general, I mean, 5 by 5 matrices is not particularly large, but in general, computing eigenvalues of n by n matrices can be very compute intensive. So those would be particular sets of things that one would think of running it not on their local laptops, but maybe on a HPC cluster that or on the cloud, or a shared VM that actually has more compute resources than just a simple local laptop. Okay. So basically, building Bohemian matrices is trivial. Like, I mean, we are building 5 by 5 matrices by randomly choosing from this 3 integers -1, 0, and 1. So we just choose 25 times from this list and then reshape that into a 5 by 5 matrix, and that's what NumPy gives you. So now let's just compute. So the task at hand is to compute lots and lots of these matrices and compute the eigenvalues and actually and plot them in the complex plane to actually see if there's any interesting patterns that emerge. Okay, and a covalent could be very easily leveraged for this. So let's take a look at how the workflow for this Bohemian eigenvalue problem would look like. So it's pretty simple. It's just very simple tasks. We just generate a random matrix. The inputs to this electron or task is the integer set from which these matrices, matrix entries should be randomly sampled and built, and the size of the matrices, the number of rows in the matrix, and the number of columns in the matrix. And this electron returns a Bohemian matrix. The next task is, once you have the matrix, you just compute the eigenvalues. So this task just takes in the matrix that was just generated. Using NumPy computes the eigenvalues and just returns the eigenvalues. And I see there's a typo here, so the last parenthesis should not be there. Okay, and then since these eigenvalues will on general be complex, we want to, and when we go to plot them on a 2D plane, we want to plot the real and then imaginary part side by side. So there are two electrons that are just doing that. So one is just given the eigenvalues, get the real part of the eigenvalue, and the other one is just returning the complex part of the eigenvalue. And the last one is like, since we want to compute lots and lots of this, say we want to compute 1 million of these eigenvalues. So like this electron is going to take a batch size, which could be 1,000, 10,000, 1 million, or however many times you want to compute this, and then calls those early electrons. Basically, for each batch size, it actually computes a matrix, and for all those matrices, it computes the eigenvalue, stores the results, and returns the real and imaginary part. Now, we want to submit, so this entire operation, so if you go back to this batch compute eigenvalues, is probably the most compute heavy part of our workflow. So we want to dispatch the entire thing to an offsite cluster. So in this case, the workflow is really simple. It's just a single node workflow where all that workflow contains is the batch compute eigenvalues electrons that we just built. And the input to that workflow is how many, what's the batch size of how many eigenvalues we actually do want to compute. Okay, so a bit about, so before I actually go and switch to a Jupyter notebook, let me just quickly mention, how does Covalent allow a user, once they have constructed a workflow, how does Covalent allow the users to specify which parts of the workflow need to go where? So through Covalent, in Covalent, this is accomplished by something called executors. Now, executors are plugins to Covalent, and they're available. So we have made a lot of these plugins open source as well, and they could be found in our GitHub repository. So what executor allows the user to do is pass in some additional metadata to the decorators like ct.electron. Users can pass in an executor to that electron, and that executor will tell this particular electron needs to execute where. So for instance, in this example, we'll be using a Slurm executor, and as part of this demo, and we'll actually touch base upon this in a few slides. We actually have a HPC Slurm HPC cluster setup that's in AWS, and that's what we'll be leveraging for the purposes of this demo and then the exercises. And so we will use a Slurm executor. We will tell Covalent that this batch compute workflow is the most compute intensive. I do not want to run this on my laptop, and just by giving it that executor and my credentials to, like, this is my credentials on the cluster, Covalent will take that and happily execute this compute intensive task on Slurm, on that HPC cluster, because I have more compute resources available over there. There are a lot of executors that we support, like local, but so by default, if you don't specify anything, the execution of the electrons happens locally on your laptops, which is sort of the default case. But there's a Dask executor. So if you actually have a Dask cluster and you want to submit your electrons to a Dask cluster, that's possible too. We support an SSH executor. Say there's the remote machine in the department, or that you have access to, or it's a virtual machine, or it's an AWS or any virtual machine on any cloud. I mean, you can tell Covalent to, like, okay, this is my virtual machine, this is what it is, this is how you connect to it, and then it will go and execute the electrons there. As I mentioned, there's a Slurm plugin that we already have. LSF and PBF are in works. We also have work in progress for Kubernetes executors. The other ones are sort of more specialized towards AWS Fargate and Batch. These are sort of cloud services that allow users to use compute heavy compute optimized instances to run a lot of compute heavy jobs in the cloud. And there's quantum executors too that's being worked on in Qiskit runtime. Okay, so as I mentioned, so like computing eigenvalues of large matrices is potentially very compute heavy. So we want to offload that to something that's more powerful than our laptop. And to do this, we just simply pass an executor to the lattice decorator. So this is, again, as I said, in keeping in line with doing absolutely the bare minimum code changes to an existing workflow. So we saw that our workflow initially just contained ct.lattice, but now we want to tell Covalent that take this workflow and not run it on my laptop, but use the Slurm executor and run it there. So this is my credentials to connect to the HPC cluster that we have spun up. And when this workflow is dispatched, don't run it locally, run it on Slurm. So I'll show you this as a live demo as well. But like when we connect to our HPC cluster, like, I mean, we sort of internally call it Beehive. So this is just a login node, and then we can take a look at all the compute resources that's been made available on that cluster. So we have a total of 16 compute nodes, and they're split into two different partitions. Like there's a partition that contains nodes that have exclusive 8-core 16 gigabytes of memory, and there's another partition, this RPI main compute, that contains instances that have 16 CPUs and about 32 gigs of memory, I believe. So the one thing that is sort of that ought to be mentioned here, that this is a cluster that is running in AWS. So AWS is the cloud provider and this cluster is actually running there. And traditionally, if this was like on-prem Slurm cluster, and then if you have access to it and we log in, and then if you want to take a look at the state of all the compute nodes on that cluster, on that on-prem cluster, typically if the compute nodes are idle or allocated already, the state over here will show that. The point I'm trying to make it is, in the cloud, we have a lot of opportunities for cost optimization. And what I mean by that is, the minute we spin up resources in the cloud, AWS starts charging us credits. But the demands on the HPC cluster, or the amount of, or the queues, or the jobs submitted to the HPC can vary dramatically throughout the day. So sometimes some hours on the day, the workload, the job queue size could be a lot. A lot of users are probably trying to submit jobs and get the jobs done. But other times of the day, there may not be as many jobs that ought to run on that cluster. So the cluster is probably actually idling a lot. What this allows us to do, in the cloud, we have the flexibility to take nodes offline and spin them back up on demand as the jobs keep coming in. So as you can see in the state column here, some of these nodes are just idle. So that means they are ready to go and accept jobs. But there are some nodes that actually have this squiggly tilde. That means those nodes are ephemeral. They are there if the workload on the cluster increases, so AWS will spin those instances up. But if not, then it will turn it down, shut it back down, so that we don't just keep on incurring the costs. So there's a lot of cost optimization that you can do. And we just randomly chose, some compute have optimized instances for as part of this cluster. But you can also have GPU instances in this. You can have really small instances like interactive nodes. Most on-prem clusters also have like visualization workstations, where users can log in and, if they have a lot of big data sets to process using ParaView or BMD or whatever we're sort of doing, those could also be provisioned on the cloud. And all of this could be very dynamic. It could be on demand. It could be spun up to match the load that the cluster is actually seeing at that time. Okay, so now let's just take a look at a quick hands-on demo on how this works. So this is my workflow that I just showed. So and this Jupyter notebook, I must say, this notebook is actually running locally on my laptop, but the execution of the actual job will actually happen on the Beehive cluster in AWS. So I'm just importing all the necessary Python libraries that I need. I'm creating this electron generated random matrix. I'm computing. This is my second electron that actually computes the eigenvalues. I'm getting the real and imaginary parts right here. And now this batch, so now I want to create the executor that I can use to tell Covalent that take this executor. This executor actually has all the information that you need on how to connect to that cluster on my behalf. So my username on the cluster is Venkat. The address to that cluster is, the host name of the cluster is RPI. This is the SSH key file that you should use to connect. This is the Conda environment that you should run this task in on the remote machine. And if there are any files that you'll be producing as this code is being run on the remote machine, put them here, like home Venkat Covalent. That's the directory. It will put all the log files in. And this options dictionary is all the options pertaining to Slurm. So if you have some experience writing Slurm job submission scripts, some of the things that typically you would specify is what Slurm job partition you want to submit this job to. So I'm telling you, when this electron ought to be submitted to this RPM main debug partition, I want 8 CPUs as part of the job. I'm just going to be submitting one task, and then when the job is running, just change the directory into this. And then once, with just these bare minimum requirements, you can create an executor. I create the batch compute eigenvalues electron, and all I'm telling now, so with the ct.lattice, and I'm telling use this executor instead of the local, which is the default, use the Slurm executor that I just created. Okay, so before I dispatch, let me show you. So this is the covalent UI. So I already did a test run of this. Once I do a dispatch, a new workflow will appear here, and also let me show you. Right now the queue is empty. So this is, I've connected to our HPC cluster. There's nothing running in the queue. Let me just open this on this side, and okay. So let me do a dispatch now. So ct.dispatch, that worked. So let's take a look. Refresh. There we go. That's the electron that just got submitted. And if you can see over here, Covalent went and submitted that job on Slurm. It submitted the job onto that partition RPM main debug, and that job is done now. So and then once that's done, Covalent will automatically bring down all the results that it produced on this machine back down onto my laptop. And we can, in a few minutes, be able to take a look at the results. So let's take a look at this. So this takes, oh yeah, there we go. And once the results are done, we can create a plot. There we go. So, I mean, this is why I sort of chose this example, because it's pretty compute intensive. It's a good candidate to show how you can offload compute heavy jobs to Slurm a backend, and the results are actually really, really beautiful. So let's go back to the slides. Okay, so yeah, so that's what I showed. So this is the same image. I just computed about 100,000 eigenvalues, but like, I mean, this one was computed using 10 million, and then, you know, the pattern is sort of a lot more richer. Just a quick point. I mean, if there's a really big, nice gallery, if you go to this URL, there's now a lot of different Bohemian matrices and eigenvalues that, you know, people can look at. So the gallery is actually sort of very nice. Okay. So the next aspect was, so far all the code examples that we've seen are strictly in Python, but Covalent was designed, or is designed, to be language agnostic, meaning like if there's bindings between Python and other languages, and as far as I know, Python actually has binding with a lot of different languages, or if not, then, you know, it's not that hard to find an open source project that's already out there and people have worked on to interface between Python and the language of their choice. So if bindings between Python and a language of choice exist, then workflows can be constructed such that electrons can invoke code written in different languages. And this next example is to show that if code, so I've chosen C because C is typically C++ is typically, you know, language of choice in a lot of high performance computing scenarios. So so the next example is to actually show if there's code or a Python module written in C, how you can use that through Covalent, again with the bare minimum code changes. So, and more support languages coming, like we have support that's actively being worked on in Bash, Julia. C++ is also a very popular choice. Fortran as well. I mean, Fortran is also still heavily used in a lot of HPC sort of compute heavy jobs. And since this is all open source, and you can actually go to our GitHub repo, and then actually if there's a language that you would like to see supported, you know, just please make a discussion or, you know, an issue, so that and we'll be happy to address that. Okay, so again, this is kind of like a hello world of, you know, some high performance compute in C, and especially when using OpenMP. So it's just basically computing an estimate of pi by, you know, using a Monte Carlo typing integrated to actually compute the area under the curve, area under the circle, and pi is just 4 times the area. That's the whole premise of this. So Python, like, I mean, typically when people do Python, get Python, install Python using Anaconda or Mini, the most common implementation in the world and most popular implementation of Python in the world is CPython. There are other versions of Python available, PyPython, JPython, which is a Java implementation, but CPython by far is the most prevalent. Now, the benefit of actually using CPython is because it has an incredible C API. So what that means is I can use Python's C API to create a Python module that I can import in my Jupyter notebook. And it's very simple to do that. And basically, all I'm doing is I'm including the python.h header file that gets installed on your machine every time you install Python. And I'm telling this, I want this C function. This C function takes in a Python object. It takes in two Python objects, self and the arguments that needs to be passed in from Python to this C function compute pi. That I'm declining a couple of variables, partitions meaning like how many partitions I want to divide that circle into so that I can compute the area. I'm initializing area to 0 because I'm going to be accumulating the result there. And dh is just the width of the rectangle that is going to be used in computing the area. The next line is just telling that whatever argument is passed to this compute pi function from Python, convert that into an integer and store that in partitions, because and integer makes sense because the number of partitions could be 100, 1,000, or 10,000 depending on how finely you want to partition that area under the circle. And then you're just computing the width of the rectangle by just taking 1 over that. And then that's it. And then the next thing is, once you have that information, all you do is for all the partition, you just compute the area under that rectangle and then sum it up. And then when you return that, like I know that the return of this is going to be Python is a floating point. So I just, whatever I compute for the area, and I convert that into a floating point in Python and return that. So this is it. This is just a simple C function. It's a very simple routine in C. But I want to now give this some additional metadata so that I can do import whatever the module name is in Jupyter. Okay. And the way I do this is like I'm going to be calling my Python module PyMonty. So if I want to use this C function compute pi, I would do import PyMonty in my Jupyter notebook, and then to call that function, I would do pymonty.compute _ pi. So this is what it's telling. So this boilerplate is sort of very trivial. It's telling that there is going to be a PyMonty module, and in that module, in that Python module, the only function or only method that there's going to exist is this compute _ pi method. And this is the module definition. So this is the name of the module. I've chosen not to provide any documentation, but like, I mean, if you want to provide a doc string that, and it's always a good idea to do that, you can just provide it there. And you're telling that this module PyMonty will contain all these methods. And if you want to add more methods, so right now there's just only one C function compute _ pi, but if you want to add more, you can just keep on adding lines here. And then at the end, you're just telling it just initialize that function. So just create this PyMonty function so that it could be imported in my Python interpreter or Jupyter notebook or whichever your choice is. And that's it. So now that we've written C code, we just need to tell Python on how to compile that C code and make it available for our consumption. And Python also has great support for building C extensions. So you can just write the setup.py file. This way, you just say that PyMonty is the extension that is written in C, and you need to build it. And this is the source file. And I'm just telling Python to actually just compile it with the most aggressive optimization possible. And then that's it. And then now the setup code is the boilerplate to tell Python on how to build the PyMonty module. And that's it. And then once this file is done, all you do is just Python setup.py and build. And then this will compile your C code. This will create a Python module that you can actually import into your notebook and just use there. One other thing that I would like to add to that, this is one way that you can write a code in C or in another language and interact that with Covalent. The other way, or there are other methods too that Covalent also supports. For instance, if you already have some C code that's not using the Python C API, you can still invoke that code in Covalent using something called leptons, which we are sort of not covering here. So we have covered electrons and lattices, but leptons is sort of the framework within Covalent that allows you to interface existing code that's not part of the Python C API, existing C, C++ code as consumable tasks in a Covalent workflow. And if you want to find more about that, like you could just visit the covalent.xyz and just read the documentation over there. And then there are great examples on how one can just take existing C code, create a lepton from it instead of an electron, and then just use that as a task in a Python workflow, in a Covalent workflow. Okay, and so having said that, let's just quickly run through the workflow. It's pretty simple. I import Covalent. I import the PyMonty module that I just created. Keep in mind that this is the module that has functions written in purely C, so it's going to be really fast. And everything else you see here is exactly similar as if PyMonty was a Python module. right? I just create my electron, compute pi, and then I decorate that, and then I just, every time compute pi is called, I just invoke the compute pi that was written in C as part of the PyMonty library. And then I create my workflow, and in this case, I'm passing in 3 different values, like for the partition. So like, I mean, compute pi when you partition the domain using 100 times or 1,000 times or 100,000 times, and then just print the results out. And as you can see, like as more partitions, as the domain is partitioned more finely, the approximation to pi is just going to go get better and better. So you could see that, you know, with bare minimum work, the integration with C and other languages when covalent is sort of very seamless. So that's sort of one of the, you know, the strong points of covalent, is because it interfaces so well with other languages. Okay, Will. So Will now just give a brief overview of, you know, what that HPC cluster was, or what Beehive is, and the current status of high performance computing as it stands in the cloud.
Yeah, sure thing. Thanks, Venkat. I'll just go kind of quickly over this, given that we're a little short on time here. Can you go to the next slide? So I just want to touch briefly on cloud HPC and what it is, because like in the academic community, you might not be so familiar with it, but in the broader HPC landscape, we're in the middle of quite a large transition right now. And what we're seeing is that HPC is suddenly a large focus of cloud providers. So AWS, Google, Microsoft Azure, and others are now interested in providing HPC on demand. And it's completely changing how we think about HPC and how we interact with it. And beyond that, given that it's a very difficult thing, a difficult concept to sell even, you know, there's really interesting discussions going on about hybrid HPC, where you have some supercomputer cluster, such as the one at RPI or such as the ones at different national labs, which are then augmented by cloud HPC resources. And so there's lots of interesting discussion about how, you know, data is passed around, how security and authentication works, how scalability works, how cost is going to work. And so if you're not familiar with this, you know, but you're interested in HPC trends, then I would suggest checking it out. We've gone over some of the basics already, in the sense that, you know, resources are just virtual templates, as opposed to traditional HPC clusters where the resources are there and they're computers that are turned on, they're all in the same room, all in nearby racks. The virtual machines in the cloud are going to be hierarchically grouped into zones and regions. So the zones are compute instances which are guaranteed to be in the same physical building, and regions are sort of groups of these data centers. So as you can imagine, if you're doing HPC, the topology is going to become very important for data transfer, so that if you're doing something that requires InfiniBand, you know, you're going to want to make sure that all of your instances are provisioned in the same zone. One of the advantages of cloud HPC is that it can, because new hardware comes online very quickly, and because there's such an enormous variety of HPC hardware, it becomes very easy to quickly interchange, you know, one CPU for another CPU. So if you're interested in, you know, how does the latest AMD EPYC processor compare to the previous generation, you know, is the change in cost and the change in availability and change in performance worth it for a particular application, it can become advantageous there. So maybe in academic research, it might not be as applicable, but in the case that you're interested in purchasing decisions for HPC, it can become very useful in order to get just a very quick high-level overview of how the latest hardware is performing. The challenge in the cloud that's different from traditional HPC is that you don't really have any visibility into the actual load on different data centers. This is a closely guarded secret in most cloud organizations. So what this means is it becomes very difficult to actually understand where to deploy your tasks. And so this is like an active, let's say, research challenge or operational challenge in cloud HPC, which is understanding, you know, if you have multiple clusters, perhaps a dozen of them, all virtualized in the cloud, how do you know where to send tasks such that they will be accepted and not rejected due to resources being unavailable? I'll gloss over the other points. we can come back to them later. But could you go to the next slide? So what we did is we developed a prototyping tool that we've called Beehive. Venkat alluded to it earlier. This is something that basically the two of us developed together. And what it is it's a Slurm federation with a Jupyter Hub front end. And so really we were interested in understanding, like, suppose you want to do HPC, but you don't have access to any clusters, but you do have a cloud account. What's like the bare minimum that you need to do in order to deploy a multi-user cluster? In this case, with a nice front end and a nice back end, such that you can like test out different HPC configurations, but without investing lots of operational time. I'll mention here that we deployed one instance of Beehive across 4 different zones last August. It has required almost no maintenance over the past year. So that's actually very surprising. Next slide, please. I won't go too much into the actual architecture of it, except to mention that we use 4 different Slurm clusters. Each of them, you can imagine, resides in a different data center. And then through the Slurm Federation capabilities, we have a master controller in one region and then sibling controllers in 3 other zones. And so what this means is that you submit all of your jobs to the master controller, and it will then in turn decide whether or not to send it to compute instances in its own zone or in one of the 3 other zones. All of these clusters are going to be connected by a shared network drive, which is this EFS mount. You can think of this as just like a NFS mount, if you're familiar with network storage. Of course, the disadvantage is if you use it improperly, you can have severe networking delays due to data being transferred between entire data centers. So that can be quite slow. The other kind of interesting flourish on this is that there's an interface with AWS Bracket, which is the quantum computing platform on AWS. So using this platform, you can interact with classical compute, but you can also interact with 8 real quantum computers that are available right now. And so it's very useful for quickly trying out different quantum algorithms that we develop at Agnostiq. Okay, next slide. So I want to just very quickly mention, how did we configure Beehive for this tutorial, just to give you like a real clear view of what we're doing. So we have a configuration file on the left that's describing the instance types, the partition names, how many instances, where it's going. And then we have 5 commands, they're bash commands on the right, and that's it. That's all you need in order to deploy this cluster. So really it's as simple as it gets. You create a network stack, create the clusters, federate them, set up Jupyter Hub, and then start adding users. So really it did not take me very much time to set this up. Next slide, please. Okay, take it away, Venkat. We have 20 minutes left.
Okay. So initially we actually did plan. So now that actually we were sort of running a little short on time. So Bill, maybe I'll just go over this section and then explain how this could be done through Covalent rather than working through a sort of a tutorial format. So so basically this last section was initially designed by us to actually be a more hands-on kind of tutorial, but all the material that we are sort of presenting here and all the material that I'll be presenting in the subsequent slides are already available in GitHub, and the link to the repo can be shared as part of this presentation. Okay, so just to sort of give a quick overview of like what all is going to be required, what all is required today for someone to actually just go and start using Covalent for now. So we guarantee that Covalent works if you have Python version 3.8 or less installed, and the easiest way to do that is just install Miniconda or an Anaconda distribution on your workstation of choice, and then you create a Conda environment with Python version 3.8, and the command to do that is just conda create, and then the name of the environment, I'm just choosing to call it RPI, and then you specify that the version of Python that I want to in this environment should be 3.8. You activate that environment, and in that environment you can install Covalent, Jupyter, and SciPy. So these are the 3 dependencies that you would definitely need Covalent to actually to dispatch and interact with Covalent. And the other dependencies are if you want to follow along with all the material that's was presented so far, as well as that's going to be presented as part of the next upcoming slides. And then once that's done, to start using Covalent, you just type Covalent start, and it will print out a URL where the UI is running. You can just go to that URL and you can start dispatching tasks, and you can start taking a look at workflows. If you want to log into the Beehive cluster, like, I mean, we have created usernames. I think every one of you is attending. Actually, your username is going to be the first 2 letters of your first name and then the last 5 letters of your last name. And then whatever password you set upon first login becomes your password on the cluster. And then if you want to test these tutorials, and if you want to test the remote Slurm executor, you need to add an SSH key to your account on Beehive so that the executor can use that and remotely and non-interactively start submitting and offloading whatever tasks you tell Covalent to the AWS Cloud Beehive. And it's possible. Right now we don't support passwords because it's not as secure, but you need an SSH key because it allows you non-interactive access to the cluster. Okay. And so we chose, this last example, I mean, we sort of chose molecular dynamics, because it's sort of MD in molecular dynamics is sort of from in its bowels itself is very workflow oriented. I mean, there are discrete set of steps that go into every single simulation that don't change, and that fits extremely nicely with Covalent. And so a very high level molecular dynamics is just a technique for studying physical systems or at atomic level using computer simulations, and basically you're coarse graining all quantum mechanics, quantum degrees of freedom, and you're treating the atoms that you're dealing with in the simulation as classical particles that interact through the Newton's equations, that interact to potentials, and then that equations of motions are governed by the Newton's equations of motions. And then once you have that system and once you have the interactions defined, you just evolve the system forward in time by solving the numerical equations of motions. And if you want to do analysis afterward, you can choose to save the snapshots of what the system looks like at various points in time to disk. And there are great open source tools already available out there, like Amber, Gromax, and LAMPS. Maybe some of you might already be familiar with it. I mean, these are great open source and molecular dynamics simulator, and actually have excellent support for doing an excellent performance across machines and across simulations. Okay, so simply, as I mentioned, like, we're not dealing with any quantum degrees of freedom. They're treated as collection of classical atoms that interact with each other using potentials. There's already a well-established set of open source potentials, like the charm force field actually has great potentials as we want to study biological systems of water molecules, for instance. LAMPS also has great style pair styles as well, that, and if you just follow these links, you can get to see a list of all of the potentials that are available. As part of this simulation, we'll be just using the simplest of all, which is the Leonard-Jones potential. And even though it's extremely simple, but it's still widely used when simulating a lot of soft matter systems like polymer metals, nanocomposites, and even sometimes in biological systems as well. So the thing is, now once you've defined the interaction potentials, you just need to tell where in space or what are the confines within which the simulation ought to occur. So that's what the domain refers to. So it's just the spatial region in which the simulation is carried out. And it also sets whether the simulation is 2D or 3D. As part of this example, we'll be just doing a 2D simulation. And the boundary conditions, and you also specify the boundary conditions that go with that domain. So are there walls in your simulations? Are there like any boundaries where the atoms cannot cross? Or is it the boundaries moving if you're trying to simulate a shear, or if you're trying to deform your system, like what sort of boundaries moving? And the last one that's most commonly used, and that's one that we'll be using too, is periodic boundary conditions. So it's a bit of blurb on what PBCs are, is they're used extensively in molecular dynamics simulations. The reason being, like, to simulate any physical system out there, like, we'll have on an average Avogadro number of particles in it, like that's 10 to the 23. That's infeasible, and that's computationally impossible for any machine on the system to simulate. So the trick is to actually study a small enough sample of that in a way that is representative of the entire system, and periodic boundary conditions allow one to do that. Basically, all it's doing that you focus on a very small subset, which is the cell in the center, and those are the number of atoms that we will be simulating. But you compute the interactions in such a way that mimics a much larger system. And periodic boundary conditions are, when you implement periodic boundary conditions, is a way to do that. Okay. And the way to do this is, for instance, like, I mean, the way periodic boundary conditions, the interactions are computed when such a boundary condition is imposed is, if any two particles, say, if you look in the red box, if the distance between any two particles is greater than half the cell distance, instead of computing the interaction with the red and, say, for example, this particle, you would compute the interaction of this one with its periodic image out there. So this is the way you're sort of imposing that this is a self-replicating structure, or, like, this is just a small microcosm of a much bigger system by doing these minimum image conventions. Okay, and so that one also, now this is where we sort of get into the workflow oriented nature of molecular dynamics, because once a system is created, once the potentials have been defined, once the simulation domain has been defined, the periodic boundary conditions have, like the boundary conditions have been defined, one of the first things to do is to actually relax the system, because any configuration in which you would create a system, if it's random, the potential energy could be really, really big, right? The system could be very constrained on a energy state that's really, really high. So we want to minimize the total potential of the system. And typically for this, like, the gradient descent is typically used. So it's a very popular algorithm. A lot of these MD integrators actually have gradient descent built into them. And all it does is it actually iteratively changes the positions of the particles in a system such that the potential energy of the entire system goes to a local minima. And once that's minimized, then you can sort of start doing your time integration and then start collecting data. Okay, and this the time. So the next step is, after the minimization, it's just time to just integrate the Newton's equations of motion. And typically the most used integration scheme is the velocity Verlet integrated scheme. That's part of all MD integrators by default. And the reason that is really great is because it's really stable. It's numerically stable, so you can do really, really long runs with it, and it's energy conserving. It's energy conserving, and it's also very efficient. And it also updates. So in efficient in the sense that it actually Wilson tried, it actually updates the forces and particles in a very computationally efficient way. Okay, and so this is the workflow. So this is the generic workflow in MD. You initialize the system, you set up the potentials, or you define the potentials through which the particles in your systems are going to interact. You minimize the system's energy by changing the particles' positions so that the entire system is in a minimum energy state. You give the system a little kick by initializing the particles with a random velocity, and then you just keep on doing velocity Verlet for however many time steps that you want. And you can periodically choose to save the positions of the particles as to disk. Okay, so this is where, but like, so I don't think, given the constraint on the time, we won't have a time to do a hands-on, but I can definitely show you the slides. And be mind, like, I mean, this notebook is also made fully available, and it's going to be on GitHub. So if people want to take a look and start playing with covalent using molecular dynamics, this tutorial, the notebook is available. So basically, first thing is you just create the potentials that we're going to be using. As I said, I will be using the Lennard-Jones, and I'm just creating the Lennard-Jones potential class that takes in a couple of parameters. The epsilon is the interaction strength, sigma is the length scale over which the potential acts, and then the cutoff. So basically, it's all this cutoff is saying is if two particles in the system is greater than 2.5 units away, they don't interact. The potential is a 0. So it's a sort of a trick to actually save some expensive compute. I'm doing all the necessary imports here. This is just me plotting what the potential looks like. So no surprise, this is like the typical Lennard-Jones potential. The minimum is at -1. The 0 crossing is at the sigma length scale, which is set to 1 in this case. And to compute forces, you just take the negative gradient of that potential, and then we can take a look at, once we compute the force grows really, really quickly as the particles come near each other, but it's attractive over a certain range, and then it goes to 0 as the particles move away. So I mean, it's in this case, since the Lennard-Jones is a very simple example, we know the closed form expression of what the potential is. So computing the analytical derivative of this potential is not hard. But in typically, to keep things consistent, or keep things quick, you can just use a finite difference to actually approximate the derivative of the potential so that you can compute the force reasonably well. So this is what I've done. In this case, the MD force is just a Python lambda function. It takes a value r at which the distance at which it should compute the force, and it takes the potential, and then it just uses a central difference scheme to evaluate the derivative of the potential at that location. And with that, you can see that, the difference, if I do it this way, the difference between the finite difference approximation and the exact one is, for all practical purposes, pretty negligible. And then you can see what the error I'm making. It's always, it never grows more than 10 to the minus 6. So it's not a bad first order approximation for the force. So now you set up the domain. Now I have an abstract class to actually mimic a particle, because in our simulation we're going to have n particles, and all the particles in our simulations are nothing more than an instance of this class. And this class contains an ID, the mass, the position, the x and y coordinates of the particle, its velocities, and the forces acting on that particle. And these are some special methods that help facilitate comparing particles, or computing the distance between two particles. And then these wrapper and string dunder methods are so that we can easily save these particles or snapshot the system. This helper method create particle just creates n particle, creates a particle, and it creates a particle uniformly distributed in the domain that you pass in. So I have a 2D domain, so it's going to assign the x coordinate to be a uniformly chosen variable between x1 and xi, and then same for y. Okay, and this is how you would implement the periodic boundary conditions, by checking whether the two particles are away. If the distance between two particles is greater than half the cell size, then you compute the interaction using its image to implement the periodic boundary conditions. And now this is a routine to compute the total potential energy of the system. And if you can see, I'm now actually even decorating these things as electrons, right? Because I want these to be distinct aspects of my workflow. So this is the electron to compute that given a system of given a snapshot of particles, given the potential and the domain, what is the total potential energy of the system? And this is what I want to minimize. So in order for me to minimize this using gradient descent, I need a way to compute the gradient, or how total potential energy of the system changes as these particles move. And this is the electron that actually does that. And then lastly, this is the one, if I want to, as the simulation is running or progressing, I want to save these snapshots to file. And then this is the electron to do the gradient descent. And so this is the electron to actually, given a system of particles, minimize the system's potential energy using the total potential energy electron as well as the gradient over here. And then once it's done, you initialize, you give the particles a small kick, you initialize you give a small random velocity to each particle in the x and y directions. Update forces is the routine, is the electron that actually computes all the computes the forces on each particles due to its pairwise interaction with everything else in the system. And lastly is the velocity Verlet integration scheme. So this is the integration scheme that you would use to update the positions and velocities on the particles due to the forces that are acting on them that were just computed using the previous electron. Okay, and finally the run method is just carry on. All it is just telling that, okay, just carry on the velocity Verlet integration using a time step dt for n steps, and n steps is going to be an input. So if you want to do the simulation of 1,000 steps or 10,000 steps, I mean, that's what n steps would be. And after each step, you just save the snapshot. You just snapshot the particle to disk. Okay, and that's it. So now that we have defined all our tasks or electrons in our workflow, you just build the simulation workflow. In this case, I'm just calling my workflow simulation, and it's decorated by the CD lattice. Inputs of this is the particles that need to be simulated, the domain in which the simulation needs to happen, what is the interaction potential, how long the simulation needs to happen, and where on my system I want to save those results. That's it. And from in this simulation, I'm just calling all the electrons that I have defined above. And this is the simulation that I would like to run. So in this case, I'm creating a domain that's 20 units long in X, 20 units long in Y. I'm just simulating 10 particles for now, and then I'm going to do it for 1,000 steps. And then when I do a dispatch, let's take a look at covalent. Oops, there it is. So my simulation is done. So it minimizes system energy. It generated all the particles, it created the initial velocity, and it ran the simulation for 1,000 steps. Okay, so let's go to Jones again. Now let's take a look at the results. So these are my 10 particles that that were used in the simulation. Now I can actually animate this, and then we can take a look at how this looks. So that's basically a system of 10 particles interacting through the Lennard-Jones potential. And there were a few tasks that sort of we also highlighted in the slides. I believe we won't have time to go through that, but as I mentioned, all these slides and tutorials and examples are made available on our GitHub repo. So if users, you can feel free to play with these exercises on your own time. So if at this point, I mean, I think Will, we're done. Like, are there any questions? We'll be happy to take in any questions or feedback. And since Covalent is open source, we really like the community to be engaged. So please do go to the GitHub, and if there are things that you would like to see implemented or you want to contribute, it's always welcome. So that would be all from my end. Will, if there are any questions, we can sort of take it now. Thank you.
Thank you so much.